All right, let's do this. So, welcome guys. Here's what we're gonna go through today. I'm gonna do a lecture called Your First MLOps Pipeline. And what that's gonna look like is hopefully an overview of what everything other than the AI model looks like when you need to actually put it into a product. That's what we're gonna go through. So we've only got 2 hours, so I'll really try and get at the essence of these different components that we want to look at and help us to do like a maybe simplified but hands-on practical illustrative example in Python from within the notebook that I'm going to go through. Everybody excited? Can I get a hell yeah?
Hell yeah.
That's right. Okay, so let's do it. So I'm Harry Berg. You know me by now. You're here to build the future. I'm from AI Core. We're the fastest growing and largest AI educator, helping people to launch their careers in the field and keeping up to date with exactly what's going on there. This is the pipeline which we're going to build today. This is an overview of what might be a simple first MLOps pipeline. So what this looks like is you got this AI model down here. And this is obviously the core thing. This is the thing that you've probably all been familiar with, been playing around with. I've seen a lot of you here before, so I know we've covered stuff on ChatGPT and transformers and been interacting with some of these AI models through the OpenAI API and more. So we've seen a lot of that AI model. That is the thing which takes in some raw feature data and makes a prediction. It's the actual, this is the tough part that we've been able to break through in recent years to actually understand how do you perform that mapping between input and output in very complicated domains, from recommendation systems to self-driving cars to image generation to language generation, etc. But when you want to actually put this into products, you're going to need a lot of other infrastructure which surrounds it. And so that's what I've got illustrated here in the diagram. It's not just the AI model. You can't give that to your users for a number of different business reasons and practical reasons, security reasons, and just kind of operations reasons. So you need a lot more infrastructure. This is certainly not a comprehensive picture of everything that you could have, but it should give you an idea of some of the key other pieces that go into these things. So what have I got here? I've got a user on the left. In our case, they're going to interact with the system through Python. So what we're going to build on the right-hand side is basically going to be stuff wrapping around an API. We saw last week, the OpenAI API is basically just a computer running somewhere in the cloud. You can make requests to it, and it gives you back a response. And there's not just AI processing happening in the cloud, but there's other stuff too. And that's what else is in this diagram of the cloud. So I've got this fast API set up here. That's what the user's directly interacting with. When they hit that API, we're going to need to add some logging into what's being made requests for, how is our server health, CPU utilization, etc. We want to be able to monitor that stuff so we can understand and see how are things changing over time, get an idea of what our customers are using it for, get an idea of how we could make our system more robust or scalable. And if anything does go wrong, trigger alerting off the back of that, so that we can be informed of whenever anything goes out of bounds or we might need to take some action, and there can be a number of different reasons for that. And if you get an alert, you might need to trigger retraining. So if you've been with me for a while now, you've only seen the kind of, train it once and then hope everything is good. In practice, a lot of the time, whatever you build before you deploy it is not going to be something that performs indefinitely over time, especially if you're working with domains where data can change rapidly or just evolves over time. If you're building a recommendation system for social media feed rankings, of course, trends and what people want to see, what the kind of distributions of people are posting, text and image, that stuff's going to change. So you're going to need to be able to keep on top of it and update using recent data to retrain the model. And in this setup here, which I've illustrated, you might decide the time to do that is when I get an alert that things have gone out of bounds of what I've trained on. So that's the retraining. And then finally, the redeployment over there to the fast API. So that kind of simple end-to-end system is an example of what you would call MLOps. I've said it a bunch of times. I've used that jargon already. I've even named a lecture about MLOps, but I haven't told you what it means. Anybody aware of the term? Understand what MLOps means?
Machine learning operations.
Machine learning operations, exactly. And what is that? Any idea? Kind of given this context so far, how would you describe that in a few sentences?
I guess user friendly and a platform to actually to give input and to get output in an interpretable way.
That's yeah, two really good words there. I like the platform for it, and the user friendliness of it. So when you say user friendliness, what we're talking about here is like the user friendliness for the people who are building the AI models, right? How do you make it easy for them to not only build a model and deploy it once, but how do you get them to do it over and over again so that it's systematized? So that's like you can operationalize that continued process of rolling out new machine learning models. I will make a kind of disclaimer, which is that the MLOps pipeline is something that's rather new in the last few years. A lot of people get very excited about it, but a lot of time you don't need it, and a lot of time this begins to have more than marginal value when you're at like really big companies, is what it seems, because they're the kind of companies that have a lot of data and have a lot of customers, such that redeploying models is actually significantly useful to the bottom line. Whereas if you're trying to build a prototype, trying to build a proof of concept, show that people want your product, probably not something you need to develop immediately, unless your product is an MLOps pipeline kind of platform. And that's the second word you use, which I really like, which was the platform. So this MLOps engineering, a lot of the time, is done by kind of what you might call platform engineers, and there's big confusion between everybody in industry and engineering of what these names and job roles actually mean, but you might hear all those kind of terms mixed together. Platform engineers, machine learning engineers, MLOps engineers, even DevOps engineers, and those kind of things for machine learning applications are building pipelines like this. So I like to say that machine learning operations, MLOps, is to AI systems as DevOps is to software systems. Can anybody give me an illustration of DevOps, David, nodding your head?
Use things like Circle CI and then deploy to a Kubernetes platform. We have a DevOps team managing that infrastructure for us.
Brilliant. Yeah, exactly. So David said you've got Circle CI, you've got some CI/CD pipelines that are continuously deploying things to Kubernetes, and the DevOps engineers, the people who make the pieces of that. They can make that whole process automated. So when you have some new software which you want to roll out, and you don't want to have to manually deploy it, you don't want to have to manually move the files into the right place and check that it's all working, you'd have a DevOps engineer try and automate parts of that, make it easier, make it automatic, and make it triggered at the right point so that it's very easy, very user-friendly for data science teams to deploy models and then kind of, push a button and automatically all the rest happens, that this gets into users' hands and it starts having an impact. It starts improving the product by producing better predictions. So so that's kind of how those things tie together for a DevOps team. And then the analogy is that if you are working with AI systems, you'd also need to do some DevOps, the kind of things that redeploy AI software, not just vanilla software. And so when it comes to the AI case, the reason why there's a difference in the terminology, the reason why you have MLOps engineers as opposed just to DevOps engineers on an AI product, is that there is some ML specific stuff that's required when you're working with those AI systems. We'll get into those as we go through this lecture, but you can kind of guess and see what they are from this diagram. So any questions about that diagram? Any questions about different parts of that UML diagram I've got there, or questions about what I've talked about so far, MLOps wise?
Well, why did you say that it's somewhat recent? I mean, I imagine Siri has elements of AI, right? And so surely it's like at least 15 years old problem. No?
Yeah. I mean I think what's new is the hype about it. What's new is that this coming into the kind of the household name, so to speak, within the engineering community, and probably also the change in how valuable this is, because obviously with breakthroughs in some of the the obvious breakthrough stuff which has happened in terms of image generation or text generation, it enables a whole host of new applications. So the value that businesses can provide is significantly more than it might have been over the past 10 years. I don't know about you guys, but like I still don't use Siri. Whereas there are other kind of products, like the autocomplete you get in Gmail, or the social media applications that you use every day that we get a lot of value from because they're able to do these new kind of these new kind of natural language understanding things. Cool. Yeah, not in a rush. So any more questions?
Should like if we wanted to deploy an AI model with our DevOps guy, is it significantly different from what they're doing? I guess it runs on the server.
Yeah, good question. Is it significant? Is it a significant challenge for a DevOps engineer to act as an MLOps engineer? Definitely a really good starting point. A lot of the concepts are translating over directly. So, a lot of the automated deployment, logging, and these kind of things, all that same kind of stuff happens with DevOps as it does in the MLOps stack. So, if you are a DevOps engineer and you want to become an MLOps engineer, you're in a great position because a lot of that stuff translates over. But on top of that, there is some ML specific stuff that you need to know. And it's evolving like really quickly, and you can get really deep into it. Today, I'm just going to cover kind of the high level, point out some of these key things which are different. So like here, kind of different types of logging, including logging metrics about your model during training. With regular software, you don't have any of that. You don't have any training. You don't have this model artifact which you need to save, and that kind of thing. You've got logging of how it's being used, logging of model inputs and outputs, and then monitoring the changes in those things to make sure that you're not kind of, as I keep saying, going out of bounds of what you can perform in. And then the alerting is kind of specific to the ML model. And then the retraining, so it kind of brings in that machine learning understanding aspect, and then deployment. So those are just some of the pieces which are a little bit different. Cool, great questions, guys. Anything else? Cool, well, let's do it. So, not that's the wrong slide. Must be another slide in here. Nope, okay, there's no other slide in here. But what we need to do is, I want to open this thing up in Google Colab. So when you get it up, it should look like this. The shortcut to get here is in Discord. If you're in Discord, go to the events channel, click on this link. Is anybody not able to do that? Good, very happy then. I don't have to show you how to get it from Colab. So go to Discord and hit that link. If you don't know how to do that, please don't sit there in silence. Great.
Sorry, I haven't joined the Discord.
The best way to do that is to kind of go the other way around. So if you go to, I don't know if you guys can see this well enough. If you go to GitHub, find my username, github/life-efficient. It's this one here. And then you can go to my repositories. And in there, you can see the most recent one is your first MLOps pipeline. If you click in that and go to the notebook, this is the notebook that we're going to go through today. You can hit here to open it in Colab, and there's a button that you can click to join Discord. It's a new feature I've introduced since last week. Great. So take a second to open that up, give me a break from talking, and then we'll get started. Okay, so today, I think we're going to get a lot of chance to code. So I want to kind of get through me talking and make sure you guys can get hands-on with these with the different parts of this pipeline. So the aim for us today is to build several common components found in MLOps pipelines and illustrate the essential concepts of this MLOps stack, so you can understand what people mean when they talk about the different phases of this pipeline. So yeah, just kind of disclaimer, this is definitely not a comprehensive overview. It's really just like to illustrate the points, because this is a very big field. I could spend weeks talking about this, and we're not going to get into using any or many of the third-party tools which can do a lot of the stuff which we're going to program ourselves they can do a lot better because they're specialized for that. But what we're going to do is just kind of highlight the point through Python, and I'll highlight resources to let you figure out how to use the third-party tools which are really popular in production. One other thing we should all do now, please don't skip this step, is you'll need to upload another file to Colab. So you can find that file here in this blue link. Click that button. You need to get the production data.py file. You need to download that with this button over here. On the right hand side, there's a button to download. Please download that file. I've got it in the bottom left there. And then upload that to Colab. So on the left hand side, you can hit that file explorer. You can hit this button to upload. And then in your downloads, you can upload that. And then you've got it on the left there. So take a moment to do that. Yeah, just follow the instructions in here, basically. It says to run this file in, to run all the code in this notebook, you need this production data file. So go to that blue link there. Get the production data.py file. Click into that. On the right hand side, there's a download button. You can download that. Once you've got it, go to Colab, click on this file, on this folder on the left for your file explorer, hit this icon to upload, and then upload the file. So you're on this page. Yeah, there's a download icon on the right hand side for me there. If you can't get it, hit raw, and that'll take you to a page which just contains the file. So just Control S or right click, save as that file, and that'll save the file. We won't need this immediately, so if you're struggling with this right now, don't worry about it too much. But we'll come back to it when we get down to the point where we need some production data which looks slightly different from our training data. Cool. So feel free to read through that description there. It's basically just me explaining what I did on the slides. But again, this is the pipeline which we're going to try and implement today. So we've talked through all of that. There's a lot of description to go further detail. I've got a data set which we're going to work with in this file. It's on GitHub, so you don't need to download it because the code is set up to get it already. But basically, what I want to imagine is that we are an online retailer and we have an offer which we're going to send to people after they make a purchase. And what we want to do is find the people who are going to actually use that offer, because maybe for some reason it costs us to give everybody the offer. So we want to send it to the best people. So given some features about how they use their most recent purchase, I want us to predict whether or not they're going to be the right person to receive this offer. And so I've got two features that we're going to use. That is the rating that they gave to their most recent product purchase and the delivery duration. And then the label, which I want us to be able to predict, is what our machine learning model is going to map the features from to predict, is the label, which is whether or not they use the offer. So I have a data set of past customers who all ordered products, they left a product rating, we tracked how long their delivery took. We want to know, did they use this offer? So that's what the data set looks like. So we can look at that data when it comes to it. And the point which I want to make here is that this is kind of data which might change over time, right? And this, when we get through my narrative, which I've constructed, is going to be the reason why we need to monitor it. We need to alert if systems go off track, and then we need to retrain on recent data. So take your time to dive into those, dive into that description up there. But to start with, you guys can just run this cell. This cell, make sure you understand it, read it line by line. It's just going to read data from a file on GitHub, and then it's going to drop one of the columns, leaving us just with the features. And to get the labels, it's going to index out that column, and then it's going to return both of those things. So I'm going to run that cell with a shift enter. And there you can see the data. Don't worry too much about the values of it. It's just a constructed example, but it should illustrate the point. Any questions about dataset? Cool. Yeah. So everybody else, just take a look at that data, understand what format it's in, play around with it, print different parts of it if you want, see what you can do with the pandas data frame, which is the data type which these come out as. But again, for anybody who missed the downloading the file, which we're going to need later, actually we'll do that one-on-one in a bit. We'll have time for that. That's totally fine. So cool. That's what the data set looks like. So firstly, in this diagram is the AI model, right? What goes into training this AI model? I want to run through this stuff quickly. You may not have seen this exact setup before, but just to illustrate the process, preparing the AI model goes through these different things, right? You go through data preparation, you go through model training, you go through hyperparameter tuning, that is setting the configuration of your AI model. You go through validation set evaluation and then test set evaluation. And so this is what I want to get into here. Cool, right. I thought I'd left more for you guys to do up to this point, but we got to go to the next cell for you guys to code. So this cell, just read through it. It looks huge, but it's just because there's a lot of variables being created. It splits up the data into different data sets. Quick reminder, can anybody explain why we split the data up?
Because we need a training set and a validation set.
Cool, and yes, and why do we need those three? To avoid overfitting. How do we use those sets to do that? Mm-hmm. Okay, and what about the validation set? Where does that come in? Tough question. Also hard to explain, so you get a gold star if you get this one.
So wasn't it on the test set that you finally kind of tune your hyperparameters and everything, and then on the validation set you actually test the performance of your model given the hyperparameters you chose?
The other way around,
okay.
But yes, exactly. So you train the model. You probably train a variety of different models with different configurations, different hyperparameters. You evaluate them on the validation set to basically say how well is this going to perform on unseen data, because those models so far haven't seen the validation or the test set. So the validation set, results, the evaluation on the validation set gives you a measure of how well is it going to perform on unseen data. You can use that to compare a lot of different models. And then you can make a choice about which one you're going to use based on which one scored the highest in the validation set. But by choosing a model based on the validation set, you're overfitting to the validation set because you're using that unseen data to make a decision about the model. So it's no longer unseen. So you can't report the performance of the model based on its validation score because obviously you've selected the one that has the best validation score. So as you said, the final result, what you report of how good the model is, how good we can expect this to do in production, is how it performs on the test set. Cool. good recap. Not the focus of here, so don't worry too much about that. If that's not totally clear, I'll be happy to talk it through with anybody once we get there. But if you run that cell, you'll create all those variables. It'll split up the data. It's loaded it in from GitHub, and then we can get on to the next cell. I'm skipping over a bit here, but in this case, I've just got one function. It always returns you the same hyperparameters. So we're going to use a machine learning model called a decision tree classifier. It's a very simple but effective model. And these are some of the different dials which you can change on it. It's just a big mathematical function, basically. And that function is parameterized by these things and others. If you want to see more about that, just hit the link above. But for example, the decision tree classifier, it takes in the max depth, max sample split, and the min samples leaf. So those are three different dials, three different parameters which you can tune for this model. So in our case, it's just spinning out the same ones all the time. What you would probably want to do is have some code which systematically changes those, produces new hyperparameters, and you train a model for each of them to see how well it performs. And then you pick the one which performs best in the validation set. In our case, we're just going to have one. So bonus challenge, if anybody gets bored at any point, you can implement that. So if we run this, we get some hyperparameters in a variable called hyperparameters. Zoom in a touch more. And then we can use those to train the model. So this part is up to you. The first line, I'm importing this machine learning model, the decision tree classifier. And in here, I need you guys to, firstly, create the model and pass in the hyperparameters as you do that, and then fit the model to the data. So check out the documentation if you don't know how to do that. Otherwise, figure it out with somebody next to you, bunch together so you can work on that. So we'll give that 10 minutes. I'll come around and help any issues that there are whilst we do that. Okay, so let's keep moving. So, my friend, in the white, how did you figure out how to do this?
Just, I don't know, it passes, so model equals efficient classifier and this.
Okay, and you said unpack the parameters. How do I do that? Oh, very nice. Okay, how do I do it? Come back to that in a second. David, how did you get this? Huh? Okay, very cool. All right. So the slightly longer but perfectly fine way to do it is to take this hyperparameters thing. Actually, I'll just show a common issue, which would be you try and do this, right? So I've got this hyperparameters thing, which came straight out of this function. What data type is that? Somebody quickly call it out. It's a dictionary, exactly. So this thing is a dictionary of the keys, which I know appear in this documentation. And so some people have tried to pass in the hyperparameters as the only parameter to this class. The trouble is that if you look at it, well, the trouble is that doesn't work. So if I run that, I get an error, and it says decision tree classifier takes one positional argument, but two are given. So the issue here, well, it becomes quite clear if you read the documentation, right? So anytime you run into an error of something you thought would work, but it just clearly doesn't, check the documentation because it's probably described in there. So if you read the call sign for this class, you can see how it should be called, and you can see if you look at the parameters here, or even look at the parameters in the next section, there's no parameter called hyperparameters. The parameters are the actual keys of the dictionary, which we've got. So I can't just give it this dictionary and expect it to know what to do with it, because the first positional argument which it takes is not hyperparameters. So what I need to do is I need to unpack it. So what do I know about this decision tree classifier? I know that it takes these different parameters, as I can see here. So one of them is max depth, and that's one of the keys in my dictionary. So I'm going to say max depth equals, then I'm going to get my hyperparameters dictionary and index out the max depth, like that. Whoa. So that's me passing in that first parameter, which I can see from the documentation, that is a parameter of this class, of how this class is initialized. So class name followed by brackets, I'm initializing it, and I'm passing in the max depth there. I could similarly do the same for the other keys as well. So what other keys do I have? I've got min sample split. And I've got min samples leaf. Okay, so now I've unpacked that dictionary just by hand. I've indexed the dictionary, asking for that max depth, for the value which corresponds to that max depth key, which in my case is 4. And then I've passed that in with a keyword argument on the left. So if I run that, it works. I get a green tick. You could probably print some interesting things to see how well it's doing. And there you have it. I've passed those things in. But this is kind of, quite repetitive and seems a bit redundant. It's like I gave you the dictionary, it already has the right key names. I wish I could just unpack that dictionary key by key and pass them as a keyword argument. So does anybody know a real quick shortcut to do that? Again, my friend in white, I'm sorry, I don't know your name. Sing, cool. How do I do this? Nice. Perfect, yeah. So really cool trick, a bit more of the advanced Python there. Star hyperparameters or star dictionary in general. Put in the function into the position of the arguments of a function. We'll take that dictionary and unpack it key by key. So it takes the key and then sets the value equal to that to the keyword argument when that function's called. So running this is the same as running all of this. Again, what the star is going to do is it's going to quote unpack it. And what that means is it's going to go key by key, index out that key, and set this keyword argument equal to the value from that key. So another really neat way to run the same code. Really compact, very Pythonic. So the next step for you guys to do for 5 minutes is to figure out how to look at the accuracy of this model. You need to import something from sklearn and then predict labels for the test data, which you're going to pass into this function, and then compute the accuracy and print it. If you do that, play around with the hyperparameters as well and figure out what gives you more performance.
Can you scroll up to the previous?
Mm-hmm. Yeah, there's the previous code.
But the fit model is not implemented yet, is it?
Which one, sorry?
The comment that says fit model 2.
Oh, yeah, perfect. And how did you do that?
Model.fit.
Model.fit, yeah. Incredibly easy to train these systems these days. You know, there's a lot of complicated stuff going on under the hood there in this sklearn Python library. A lot of code written by a lot of smart people, and all I have to do is to write that. It's very simple. Takes in parameters. What does it take in? What?
Features and then as a second label.
Exactly. Yeah, and that's because it's got to fit to some pattern, right? So you got to get examples, paired examples of pairs. Sorry, paired examples of data points, which is going to learn to map between. And so this is the supervised learning case where you have a data set full of both the inputs and the ideal outputs. So I'll pass in the features and the labels, which will pass into this function. And then when I run this code, I'm going to train the model with my training features and training labels. So I run that. Cool. So yeah, do the next cell, guys. And again, kind of we're building up some bonus challenges here. So one of them is to maybe try this out with different models. Another one would be try out different hyperparameters, and another one would be implement some kind of code to iterate through hyperparameters and pick the best model systematically. So take 5-10 minutes to do that. Actually, just 5 minutes. I want to blast through this model training section.
Make sure you understand that. Like, you don't need to build it yourself. We'll be able to go and figure out the parameters, but make sure that they can make sure that they can talk to you clearly exactly how it works from at least a high level. That you can use the application, see the experience, tell somebody else how it works. You don't have to build it, but you should be able to help volume system, function itself.
So, anybody got the code that determines the accuracy here? Someone call it out to me quick. Where did you import from? sklearn.metrics, you said? Nice, import accuracy score. Like that. Cool. If you didn't know that, if I didn't know that, I would just search up Python sklearn accuracy. That's what we were talking about. Okay, look, the first thing here. First thing, documentation, the same format as usual. Just scan through it. You can see what parameters it takes. You can see where to import it from sklearn.metrics. And so let's put that into our code here. So, my friend, can you continue on from there? Just these two lines. Equals model.predict. Yeah, so we got to make a prediction to get the predicted label. Sorry? Yep, so I got these two parameters coming to the function, x test, y test. I'm going to copy that exactly, actually. So those are the two parameters there. Oh, no, sorry, no. Don't need that one, do I? I just need the x test. And then what I want to do is compare those predictions with the labels which came in. How would I do that? Nice. We imported the accuracy score. And we want to compare the predictions to the labels. Y-pred to Y-test. Run that. Accuracy score, 96.4%. Not bad for like 5 seconds of code worth running at this point. So that's pretty good. A very simple data set, of course, but just highlights how easy it is to build some basic models a lot of the time with no testing or kind of systematic hyperparameter search implemented so far. Let's just guess those parameters. So that's evaluating the model. we're building up different parts of this training pipeline, right? So a quick one, did anybody go onto the next cell and figure out how to save this model? Yes? Nice, cool. So there's a hint up here, which is import joblib. And my prompt was for you to save the model to disk. We said use joblib dot dump. And what parameters does that take in? Yep. So you know, if you guys you know, if you don't know what a function is gonna do, just look it up, but also hover over it, and in Colab you'll get a prompt for the documentation too. So it says here, okay, the first argument is value, it's of type any. The second is file name, it's of type any apparently, but then the parameters are explained down here. So value, this is the object to store to the disk, and file name is the file or the path of the file in which it is to be stored. So I basically want to say, I want to save the model, and I want to save it in, what did we save it as? Model.joblib? Cool, yeah. So the joblib extension is just like it's just it's a serialized file format. Basically just means take whatever this thing is, turn it into a string, might be really long, and then that's what you can expect to find in the joblib file. So I got a red line here. Why is this? Run that. Oh, there's an extra space. Run that, cool. It seems to have run. How do I check? Look in the left-hand side. You can see in my files, I've got this model.joblib now. Can I see that in here? I don't know if I can open that or preview it in Colab. No, I don't think so. But it's probably just like a big lump of random strings it will look like. But somehow, when you deserialize that into Python, it becomes the data which is that model. Excellent, great stuff. So now, guys, just spend like 2 minutes, I think. Run through these lines. This is just taking everything we built so far, putting it into a step-by-step pipeline. The point of this next 2 minutes is just for you to understand how these things connect. How does loading in the data connect to creating the features and the labels? How does that connect to the hyperparameters? How do all those things connect to the model? And then how does the accuracy come out of that? Take 2 minutes to do that. If you missed the code for evaluation, there it is. Yep.
Earlier on, when we were talking about the validation set and the test set,
Mhm.
how like the validation set would be used first,
Mhm.
and when you start comparing reporting it, then the test set used. But it looks like we're using the test instead of validation. Does it just not matter?
Yeah. So question, why am I using the test set here? When I said earlier, we would use the validation set before the test set. It's just because I'm skipping over some points. This isn't really the essence of what I want to get to today, but just a reminder of kind of what goes into building the AI model. So yeah, the extra challenge here would be write another cell which scores the model based on the validation set, and then picks and does that for many models, and then picks out the best one, and then finally reports the best performance on the test set there. So yeah, sorry I'm missing a step here, but it's just not the most important thing for this lecture. Cool. And there's the model save code if you missed that. Excellent. Right. So instead of writing all that out, I'm just going to go to the next cell, which is all of this in a function for you. So here you can see how everything actually connects together. There's a lot of just white code written there, but line by line, we're loading the data, using that to split the features, using this sklearn function split data. We're getting the hyperparameters from the function that we created. We're training the model. We're evaluating the model, and then we're returning the model artifact and these two metrics as well, accuracy and the dictionary full of hyperparameters. And then final print of the accuracy, run that function, everything works. So this function basically does the whole pipeline. This is all those bits that go into the AI model stacked together, missing the bits which, of course, I've talked about. So you can write all that in Python, and you probably will need some Python code to do that. But orchestrating those things, making sure they happen in sequence, one after the other, potentially doing that on a big computer, potentially doing that in the cloud over a period of weeks, if it's a big AI model, is probably not going to be something that you run in a Python notebook. And so I've highlighted some of the key tools which you might want to use to overcome some of those challenges, such as Airflow, which is kind of the unsung hero of MLOps, coordinating everything. It can sequence the right steps of pipelines, including the model development pipeline, but also other parts of the pipeline too. Puts those all together, reruns things if stuff breaks, and so on. AWS SageMaker is basically Amazon Web Services platform for machine learning everything. And Databricks is basically a similar thing with a big focus on being able to store all kinds of data as well. And Kubeflow is another system which can kind of orchestrate different parts of the pipeline too. So if you want to look into taking what we've written up here, or the code, and putting that into a more robust pipeline which can run at a bigger scale, run in the cloud, etc., I would look into those tools. So now we kind of get onto some of the more pure MLOps-y stuff. What we've really just discussed is a reminder of what the AI pipeline looks like, and then that's part of the job of automating this would be to put that all into one series of steps that go together. The next thing is metadata tracking. So this is a machine learning specific part of the problem, because when you introduce this concept of having this model, which is basically just a file full of data, the parameters which define the model, then you need to keep track of that. Basically, you might want to track things like, okay, which model experiments have I run so far? Which hyperparameters and different model variations have I tried? Which data set was each model trained on? How long did it take? All these other kind of performance metrics, which you might want to look back on for historical knowledge of what works and what doesn't. And then the big one is obviously the model itself. Like, you need to save that thing, because that is actually going to be used later. That is the crux of your application. So these things need to be logged. So the worst way to log all your hyperparameters would be to come up with your own idea, right? Come up with your own implementation that saves them in different files and folders, and it's all very organized. Trust me, somebody has thought of that, and everybody has this idea of, I'm going to build my own hyperparameter logging setup. Like, trust me, just use a different service. There are plenty of those which I've listed down here. So model metadata tracking tools used in the wild, things like weights and biases, MLflow, Neptune. MLflow is pretty comprehensive. I think that's a good one, but weights and biases picking up a lot of momentum as well. But here, I'm just going to use my old favorite, simple TensorBoard to log these hyperparameters. So I'll give you guys 5 or 10 minutes to do this. This is basically go through the steps of import TensorBoard. You can get it, I'll give this one away, from torch.utils.tensorboard, import summary writer is the thing that we're going to use. That summary writer is going to be we're going to initialize a writer equal to that thing, and that writer is basically going to be something which we can write to these logs with. So I'll leave you guys to look into the documentation for that as we go through. But basically, you want to log the hyperparameter dictionaries and log this metric dictionary. So I'll go ahead and do that. All right, cool. So, writing the logs. Create a TensorBoard writer. I wish we had name badges or something. I hate kind of pointing and calling people, but my friend in the cap, in the middle there, trying to avoid me. How do I do the first part?
Yeah, it's just summary writer.
Cool. Nice. So initialize that class. And then we wanted to log those hyperparameters. How did you do that?
So hyperparameter page parameter equals parentheses parameters. I parsed like this because I got an error.
Okay. So, but this needs to be called in a function, right? We need to, like, these are the parameters for a function.
Yeah.
Right? So what's the function we want to call on them? Writer dot.
Oh yeah, sorry, writer dot underscore hyperparameter.
Yes, there we go. So lots of different things you can log with TensorBoard, but there's the add hyperparameters. Open bracket there. And then these are the arguments to that. So then you said hparam dict. Let's try that as hyperparameters, because that's what we have got, right? Is a dictionary of hyperparameters, and then a metric dictionary. How did you do this one?
So I did equals curly brackets and I created a dict inside it. So I put in a strings ACC, then column, and
Cool, nice. I like full names to remove the ambiguity, but yes, accuracy is going to be the accuracy we passed in. So just note there that the two parameters we get, this one's already a dictionary in the right format, this one's a number, so it needs to be turned into a dictionary like that. And then I think this should be good. If we run that, we get an issue because I forgot a comma there, but if I run that again, everything looks good. So now that's happened. Where's it gone? What's happened here? Where can I see visually these things logged?
in a folder runs.
They're in a folder, yeah. So over here, got a new folder that's been created when we created that summary writer and made a log to it. In there, you can see there's something with this date, and in there's even more complicated stuff, but it's just the format of the TensorBoard logging metrics. If we want to open that, oh damn, I should have included this because it'll be very easy for you guys to miss this, but just want to highlight, this is really important. If you want to see anything going forward, we need to add this line. We need to add, what is it? Load underscore extension TensorBoard, and then percentage TensorBoard dash dash logdir runs. I think that's right. Let's see if that works. Maybe it needs no space there. There you go. All right, so that I'm going to copy into Discord again in the events. Sorry, I forgot that. But once you do that, you'll get this pop-up, and this should show, oh look, something's been logged in the middle there. It's just 1 point so far. What we want to do is see that over time, but right now, that has been logged. So there it is, guys. Sorry, what is this that's been logged? Yeah, this is the accuracy that's been logged, but there's also h-params. So over here, I can see these are the different hyperparameters that I trained with my model with, and this is the accuracy that it was scored. Once I get a few more of these different models, I can get some interesting visualizations like, okay, these are the different axes for each of these different variables and the final accuracy. So you can get different lines going through this to show how it results on the end. Yeah, so we're in h-params, parallel coordinates view. So yeah, there's a few more visualizations. If we want to get some useful stuff in here, we could go back to our hyperparameters, change this a bit, you know, and then run through things again until we get to that logging. I've lost my TensorBoard. Oh, there it is. Cool. So now I've run it again. I should have, yeah, 2 records in here, highlighting 2 of the different runs I've used with different hyperparameters. And in the parallel coordinates view, you can kind of see, okay, well, if I go along this line, I get to this accuracy. If I go along this one, I get the same, it looks like, actually, in this case. So play around with that, and you should be able to see how those things fit together. My laptop's dying, so charger. Great. So so moving on from that, we've logged the data. Now it would basically be time to well, now the right thing to talk about, I think, is serving. So serving would be taking this model, deploying it, and putting it into an API, essentially. So this is the code in the next cell, which you'd put in a separate file, and you'd run that Python file on a computer somewhere. What this defines is the behavior for the API. So it basically says, if you send a request to the address of the computer /predict, it's going to run whatever's in here, and then it's going to return that prediction as a response to your request. And what you'd usually have is this line uncommented, and this running in a Python file somewhere. We can't run the API using that line within a notebook, so I'm kind of going to cheat a little bit and pretend this is running on a different computer. I'm just going to use this function. So what you need to understand and imagine is that this code is running on a different machine far away, and what I can do is I can make requests to that machine. I can send some data to /predict, and that'll basically run this function. So back in our diagram, I'm this user over here. I'm working on my own Python code, my own, on my own machine. I send a request over the internet. It runs a file, which is this file. And this code here, which is basically the fast API code, has these different decorators, which basically tell Python, hey, I'm running on an API, and I should be listening at a certain address on this computer for requests when they are sent to each of these different endpoints. And when I get one of those, I should run through this stuff. So I'll illustrate that in a second. But for now, let's take 5 minutes, 10 minutes maybe to write up this code. It should be pretty simple, but 3 things: define, load in the model, get the data, get the prediction, and then return the prediction as a list. One thing to note is that what I want to do, and what you typically need to do to send data to an API, is you need to serialize it. That is, turn it all into a string so that it's not like a complicated Python object. So what I've got here is expecting it to come in JSON format. So we can read this JSON format into a pandas data frame. Just look up pandas data frame read JSON. And we want to return it as a list. So look up pandas data frame, turn to a list. So I'll just give you 2 minutes to look into that, and then I'll run through this because this might be a bit foreign to some people, so I'll show it. But stretch yourself to use the documentation to look these things up, and that's what will really build skills. Okay, so I'm going to go through this one quickly, but just hopefully stretch your muscles there. On this line, I want to do the inverse of what I did before, which was joblib.dump. Now I want to do joblib.load, and that is going to accept some parameters. What's it going to accept? It's going to look for a file name. So I just need to give it that file name, which is model.joblib. that loads in the model from somewhere where it should be accessible to the code running on the API. So you need to package the model and send that with the API. At least that's one way to do it. So the API file can load in the model. This creates an instance of the API, and then these define the different methods which the API can accept. And so in this one, I need to read JSON into pandas data frame. Well, I've got pandas as PD, I believe, already imported. So I should be able to do PD from JSON like that, and then pass in the data there. If I'm doing that correctly, I think. Let's see if that works in a second. Make a prediction. Well, I've got the model. I just need to pass in the data. And then I should be able to return that prediction as a list. So I'll do prediction.to_list. Again, easy to look that stuff up. Just search, read JSON to pandas data frame, and then read pandas data frame to list. So if I run that, and then skip, oh no, something's gone wrong then. No module named fast API. If you get that ever, just remember you can do !pip install the name of the library that you're missing. So fast API for myself, and also that unicorn one, which we're not using, but I'll copy it anyway. So run that, should install those libraries. Now I run things, and it works fine, no errors, but to be honest, that's not much code actually run. I've just defined some functions. So do those functions work? Well, let's scroll down just a little bit. I'll come back to that one. But if we come to this function, we should be able to call the predict method on that, what I called the payload there. So this payload is going to be what you'd send to your API. It's basically some features that is that's a pandas. Sorry, it's the same format as the data that we've got above. You can look up what features is defined as if you want. And I'm just going to send that to the API. So if I run that, I get an error. So I must have done something wrong. Module pandas has no attribute from JSON. It's probably because it is read JSON. So if I run that again, redefine that function. I haven't defined that one. Run this. Okay. Now I get another issue. It says decision tree classifier object is not callable. That's because I've tried to directly call my model, not call model.predict. So that model has a function. It's called predict. If I run that again, things should work. Okay, I'm getting another issue now, which says NumPy object has no attribute to list. Okay. Again, the format you actually choose is totally up to you, but in my case, I wanted it as a list. That's just kind of how I've defined this part of my application. I simply search NumPy as list. It says to list. So all I've done there is I've added in an underscore. So if I run that again, we should get it in the right format. And then I get a bunch of zeros and ones out. And that is the prediction of my model. There's way too many of those to scroll through. But that's a lot of data I've made predictions on in parallel. But that thing seems to be working. Ran through a lot of stuff there. If you are struggling to keep up with that, you can find the solutions in GitHub as well. Okay? So if you do want to copy anything over, you're not able to keep up with that, feel free to just check out that solutions notebook. So I kind of want to illustrate this point that I'm talking about here of this code would be running somewhere else. Just for illustration purposes, it's in the same file. So if I open VS Code, let me kind of show you how that would look. So let's say like we're on a computer in the cloud, and here, this is where I want to run my API. So I'm just going to run, I'm going to take that code, which is in my notebook. The one that defined my API. I'm going to copy that into this api.py file. And that looks different. What happened there? So I'm going to copy all of this into a different file. Guys, if it's ever too small for you to read, just let me know, because sometimes I turn around and it's absolutely tiny. So I've just taken that code which we had in the notebook. I've put it into a Python file right there. And now I'm going to try and run that Python file from the terminal. So just Python name of file, Python api.py. And I actually need the completed version, wouldn't I? But what I'll fix this whilst you guys have a chance to code. But essentially what I'm saying is you should be able to run this file, and in the terminal it will say, like, hey, I'm waiting. API is sitting here. It's running. It's waiting for requests. So that's what's happening on a computer somewhere in the cloud. There's just some code running, and it's just listening. It's listening for messages which say, hey, send this to /predict, or send this to just / to the root of this computer's address. And when it gets one, it's going to run this stuff. In our case, it's going to make a prediction, and then it's going to send it back to the user. That's what Fast API does, and that's what this line would need to be uncommented for. This is the one that actually runs the API. It runs some code listening for requests, and it can respond to them. So this is kind of how you would go about serving these responses. And then you'd be able to make requests to them, as in this cell just below. So again, it won't work in this notebook, but this is how the client would make requests to your API. They would take the features, and they would do features dot to JSON like that, and then they'd run this line, which uses Python's requests library to make a type of request called a GET request to that URL, which is this. It's what is the URL of the computer that is running. It might be, an IP address. Like this could just be an IP address, so it might look like something like that. Every computer has an IP address. It's just like an address in real life. It tells you where on the internet it is, kind of hierarchically. And if it's running on your own computer, you have it as localhost, which means this computer's IP address. And on the end of that, I've got the /predict endpoint. So that's basically saying, here's the address of where I want to send my request to. It's those things stacked together. And this is how you would make a request to it, just like that. You simply make a GET request, and so this response is what the API has sent back to you. Are there any questions about that? I just want to be super clear that in the notebook, it's an illustration of just the code that you would have. In practice, you wouldn't have this API code, this stuff in the same Python file. It's running on a different machine, and so you would make a request to it and get that response back. Is there any confusion about that? Cool. I wish I'd prepared a better question to test you guys with, but for now, just in the interest of keeping going, I'll assume that everybody's comfortable with that. If you're not, it should be explained in here. If you're not, you can always let me know and I'll talk you through it. And so to kind of move on and simplify things, going forward, I'm not going to be making requests to some computer on the internet. I'm just going to be calling that function. And so again, just to really point this out, you wouldn't be able to do this in practice because the API would be running on a different computer. So every time you see me call the predict function, you should basically think, okay, this is where Harry is making a request to an API, which is on a different computer. This is the bridge in the diagram shown. God, that's a lot of predictions. Shown by the, shown by the illustration, which is somewhere obviously very nearby. Maybe I can just scroll outside that box. Yeah, that's this part here. So this cross-cloud boundary is kind of the interface that I'm talking about when someone makes a request to the API. And in our case, in the practical case, that would look like, requests.get to the URL, sending your payload. In practice, or in this case, in this contrived case, what it looks like is just calling the predict method. So every time you see the predict function, just imagine, okay, he's making a request to another computer. Can I get a thumbs up if that's clear? Cool, great. So I'm going to skip over the cells just above this, but feel free to read them if you want. I'm going to run everything before up to this point, and hope that this runs. I'm going to skip past that, just run this. So there's me logging the data. Here's me defining the API. I'm basically going to have that function, predict function, which I can use going forward. That cell won't work because it's making a request to an API which isn't running. This cell works because it's using the method defined earlier. And then just up here, again, look into this in your own time, but I'm basically just defining this Python object called API client, which has this predict method. So a lot of APIs, like the OpenAI API, for example, they have a Python library you can download, and it has functions attached to it, which you can call to use the things that API can do. In our case, we've defined an API which can make predictions. Send a request to the computer, it makes a prediction, and it sends it back to you. Instead of writing requests.get and using Python's request library to make the HTTP request directly, you can often just get what's called the API client and use its methods. And what that does is, under the hood, it will make that request. And then it will send you back things. So basically, this is what you're going to see throughout the code going forward. You can basically just imagine this is what someone would write in their Python application that is going to interact with your API. So some serving tools that you might see in the wild. Fast API is pretty popular. It's like the top API building library for Python right now, and everybody loves Python, especially if you're working in AI and data. Again, SageMaker makes an appearance. Not only does it let you do the end-to-end training I talked about earlier, it also lets you serve models in a API kind of fashion. KF serving is the kind of serving end of Kubeler, which I talked about earlier. Kubernetes is kind of somewhat underlying infrastructure that these things probably run on, which lets you create lots of instances of the same code and scale it up and down. And to do that, you need Docker. I'll leave you guys to look into those things or take questions if you want to get a little bit deeper. But to move on, the next thing is the monitoring. So we want to track. We obviously don't just want to log those metrics. We want to visualize them. So some tools you might see to do that in the wild: Prometheus and Grafana used in a pair. Prometheus lets you actually store the metrics. Grafana is a dashboarding tool which lets you log them. And then there's a few kind of other enterprise scale sort of consoles which you can log into, like Evidently, Fiddler, and Arise, which are more of like they're kind of some of the bigger players, the bigger closed source players in the space. Grafana and Prometheus are just open source tools that you and I can use for free. These are the kind of things that you'd probably need to set up an account for. So if you're interested in more monitoring, especially things like monitoring, basically everything we're going to do from this point on in an automated way, you should look at those tools. So I just want to show some basic examples of the stuff that you might want to monitor. And one of those is like hardware metrics. This is kind of the non-AI specific setup. So I'm going to install this Python library, psutil, and I'm going to implement this code, just an illustration to say you could log things like how much space is left on the CPU. Am I running at 99% capacity, or have I got like a lot more space? These kind of things we'll look at in the next step would give you an idea of like, do I need to scale up my server? Do I need to change the type of computer that it's running on? Or is it on fire or something like that? Because you can log temperature and those kind of things. So With that library, you can do things like CPU utilization. Again, if I didn't know how to do it, I'd just look it up, Python CPU utilization %, and then it says how to get current CPU and RAM usage in Python, exactly what I'm looking for. Here it is. So, just look up. There's a ton of other hardware metrics you can get from Python libraries. If you want to do it in Python, just look it up. Otherwise, look at Prometheus, which has all these things built in. So how do I use that? It just says, CPU %, and then you give it a number, which is the time over which you want to average the CPU %. So I'm just getting over the last 4 seconds. And then I want to log that to TensorBoard. So as usual, we just take our writer, which, by the way, everybody pay attention. I've put this as an attribute of the API client. So API client dot writer dot add scalar. And then I am gonna log I'm gonna log CPU utilization, and then give it a and then I'm gonna give it a the value there, which is the CPU utilization %. Cool. So, and then there's another example of how you can get a different metric down there, but just to illustrate the point, I can run this to log some hardware metrics. API client is not defined. Need to run these cells above. Okay, it runs, gets CPU utilization. So you can see in this notebook, I'm at like 35% capacity. That should match up with what's over here. Maybe not, I don't know, but similar. So that's how you can get some of those hardware metrics, kind of things you might want to log. That's very DevOpsy, right? What we probably want to log is more machine learning related stuff. But firstly, I'm gonna just add that function into my predict method. So here I'm just gonna overwrite the function, which is the predict function in my API. So you can think of whenever I do API client.predict, it's gonna use this function, and I've just updated it with logging the hardware metrics. So if I run that, and then run API client in testing mode, look at the definition if you want to understand what that is. I can just call this predict method. So I'm writing my Python application, and I want to make a prediction to this API. I send my features. That's going to run this predict function, which includes logging the hardware metrics. So what that means is when the API receives a request, it's going to log that stuff, it's going to save it in TensorBoard, and we are going to be able to track it over time and see how it's changing, and then set up alerts for when it breaks those boundaries. Looks good. I got back a bunch of predictions for the many examples which I sent through, 0s and 1s, whether the customers are going to use this offer. So you can imagine, just kind of give that context again. You can imagine that I'm working in a big company like Amazon, and I'm on a team which is to do with monetizing these offers. So you could say, right, my engineers are going to set up a request to part of Amazon's API. I'm going to send them this internal data. It's gonna tell me whether this person's going to buy or not, and I can use this. My team can use this to make good decisions, basically. So I'll leave you guys to kind of take a look at this code and implement what we've talked about just there for a second. But up to this point, what we want to do here is log the actual values that are going into the model. So this is the ML specific stuff. I want to log the input values to see what are people using my AI model for? What kind of stuff are they sending it? Another example of this might be your OpenAI, and you want to know, okay, what kind of things are people trying to make GPT-4 talk about? Do we need to be paying more attention to the anti-hate speech kind of features that we're building, because a lot of people are doing that for some reason, or do we need to be paying attention to the the misinformation kind of features that we're building, so you can see what people are using your application for. So that's why we'd want to log the kind of input metrics that go into our model. So take a moment just to assimilate that and have a go at the code, and then we'll come back and get on to the next step. So I'm actually just going to copy the solutions from my solutions notebook in, just because it might be a bit tedious to get this exactly right with the time pressure that we're under. So I'm going to come back here and just paste that in, and I'll take you through what's happening line by line. So this function is to log the model inputs. So what I'm going to do is I take the data, it's a pandas data frame. If you look it up, you can get row by row by using this method. And then I'm just using the writer to add a scalar value to my to TensorBoard. That takes in 3 different parameters. It takes in what's the current, it takes in what's the name of this thing, and I've called it product rating slash this thing, which is either going to be testing or staging. So what I want to be able to do is compare testing and staging. I'll show you what that means in a second. And sorry, testing and production. Then I've passed in the actual value, which comes into this data in the form of like a dictionary, basically. So I'm going to log that product rating. And then the API client also has a value called step, which is just like the X position I'm going to log this at. So when I run this, it defines, okay, I'm going to update my, my predict method to log the model inputs. So this is basically becoming a bigger stack of everything that happens inside the API. When someone makes a request, it doesn't just make a prediction, it does all these things around it. And so this is where you can start to see there's more to these AI systems than just the model. You know, you've got this logging, you may need to connect to other data sources to get different features. You may need to, you know, track hardware metrics, track model inputs. You may need to, you know, make sure the response is valid, etc. All those kind of things wrap around the actual model call, which is in this line. So I'm going to log the model inputs. I'm going to pass in the data there. If I run that, let's hope I've got everything right so far. Seemed to work fine. I get some predictions out. And we'll go over that in a second. But basically now we should be able to look at TensorBoard again. So if you ever want to pull up TensorBoard, just take those lines which I've passed in here, or that bottom one at least, and run that. So percentage TensorBoard -- log dir runs. That's going to open up this board here. And we should be able to see in that somewhere, if we go to scalars, we should be able to see, okay, now we've logged accuracy, CPU utilization, and these different inputs to the model. We've got delivery duration and product rating. And what the API has done is it's logged them sequentially. So it hasn't just logged them all at one timestamp. It's taken in the features, and for each one it's predicted, it's saved what the value was. So you can see the sequence of those over time in the horizontal axis look like this. So this was how the features came in during testing, or during kind of, before I've released this to the wild, or I've shown it to my real users. It looks like it's kind of, okay, it's oscillating about a point. So we know that if we smooth this out, you can see, if you smooth out all the way, you can see it stays around this value, right? So as long as our model can do well in this regime, this is good, right? What's the problem? Over time in production, models used to taking in features which are kind of in this range. These are the different values of the inputs. Problem is that over time, people might change their behaviors and start to give different inputs to the model. So in our case, the model takes in the features of the delivery duration and the product rating. Or maybe different things could happen in the real world that affect those kind of affect the values of those kind of inputs. Perhaps there's perhaps life gets really tough for people and they really appreciate even a crappy product, so they give it a super high rating. Maybe just something in the world causes that kind of behavior. Or maybe competition all increases their delivery times, in which case the standard for delivery times is going to get harder to hit. So that value which is going to come in of how your delivery time compares to what you promised might be affected. So these things can change over time as the world is continuously evolving, especially in domains where the data is naturally changing. Things like social media, that kind of data is constantly evolving trends. Things like fashion, right? It's all going through changes forever. There are domains, of course, where it doesn't change that much, or it changes a lot slower. And there's also domains where it can change not just gradually, but there can be a step change. For example, if you're monitoring machines in a factory, suddenly you get a new batch of materials, and that stuff starts coming in, and then suddenly the values to your inputs of your model, maybe it's a different color metal, maybe it's a different hardness metal, or maybe something like that. Suddenly there's a quick cutover, and your data might jump. The distribution of what your data looks like might jump to a different region. So this is the setup for the next part, which I want to talk about, which is drift. Drift is a very big term in MLOps, and there are kind of two major kinds of drift. Drift in the data, and that's called data drift or concept drift. What I'm describing there is data drift. Data drift is change in the input distribution of your features that are coming into the model. Like I said, changes in what people are posting online, changes in materials that come into the factory, change in how people are using the product over time. Those things affect what kind of inputs the model needs to be able to handle. So you need to make sure that the data you've trained on is as close to as possible what the data looks like in production. Otherwise, everything that you've benchmarked it against is not really going to be valid, because it's such a different domain. And so because of that, you want to be able to track this kind of stuff to see, is it changing? And if it is, alert someone. And if that alert is serious, then retrain the model, and so on. So what we've got in the code so far is logging this stuff for testing data. And so when we go through running all of that, sorry, it's just down here, isn't it? So we've run that on some testing data. I've got my testing API client. It's logged some stuff. I'm going to scroll down, and And yeah, and there's what it looks like, just to kind of screenshot there. But if we go down, now we want to get onto this section of looking at drift, right? So data drift is the one we're going to look at first, which is where the inputs of your model change. Concept drift is something I'll leave you guys to look into in your own time. Concept drift is where the mapping between the inputs and the outputs changes. So basically, like, has the definition of your problem changed? Let's say you're building a let's say you're building a sentiment, classic example, sentiment analysis on tweets, right? The way that people can say good and bad things, or that can change over time. Potentially, like, a new word comes into language, and that means something, super good or super bad. Like, new slang comes in, and previously that word didn't mean anything. So the input would have mapped to, I don't know, that word doesn't really mean much. Now people start using it. That input-output mapping has changed. And so that's an idea of the concept of what it means to take a tweet and correctly predict what it means. That has changed. Other examples, let's say, I think fashion is a good example. Let's say you had some application which is like, fashion score, right? It scores how good this outfit is. Well, you can take the same outfit 10 years ago, and it probably, maybe it's not a good outfit. You take the same outfit now, and it's an amazing outfit. It wins awards. And so that's an idea of the concept drift. Over time, the mapping between inputs and outputs can change. So again, summary, data drift is your inputs are changing. They don't look like what they used to. And concept drift is the mapping is changing. We can do a quick example of concept drift here using this class, which comes from the file which you guys should have imported earlier. So if you haven't done it already, go straight to the top, and there's a link to a file which you need to have in Colab. It should look like it does over here for me, production data.py. That's the one I need. And in that, there's this thing called real world data stream. Real world data stream is something I can iterate through. So just, for data point in real world data stream. And it's going to simulate someone sending me a request. Every time I ask for a new item from it, it's going to pretend that someone's sent me some data. And what you can imagine is that, okay, I've built some Python application, and my team is using it to evaluate these different people's orders and whether or not I'm going to send them an offer as it comes in. So I've got some code running, which takes in an order as soon as it's fulfilled, and as soon as someone rates the product, and I've got my measure of the delivery time, I'm going to send those data points to this API running. And that's what's happening over time. Like, people making requests using your application, and you want to make those predictions using your API. Data comes in, make the prediction, the model computes what the answer is, sends it back to me. So if I run this cell, I've set here testing equals to false. So this is going to show up in a different graph in TensorBoard. But if I run this, it's running, and it's continually running, actually. So don't worry if this doesn't stop, because there's a long stream of data in there which is being processed by our model. But if we go to TensorBoard again, we should start to see different stuff showing up. I'm going to keep it nearby. Just going to stop that for a second. I'm going to get TensorBoard right here. And then we'll take a look at the production data, which some of it should have been logged at least. I'm going to run that again so we get some more of it whilst we're looking at this. So here's TensorBoard. I'm going to go to scalars again. And in there, now, I've got multiple graphs. I've got one for production and one for testing. And what I've tried to set up here is one way that you might be able to look at the data and see, okay, does production look like much what we were testing on? Of course, it's a very simple example. I've only got two features. They're just scalar values, so it's not really that complex. And you might need to have some much more advanced visualization depending on what types of data you're dealing with. But in this case, to illustrate the point again, you can just kind of see, right, what are the values coming in over time. So this production data, I believe this is like this is still coming in as we speak, as that code is running. It's data that's hitting the API, and you can see now the comparison between those two things. So this one's kind of oscillating around the 1 mark. This production data, it looks a little higher. It looks like the data, the input data has drifted. It's drifted away from what we expected it to be. Now we can see that. That might be a problem. We should probably figure out if it's a problem. However, this model is running and it's serving users, and I'm asleep on a Friday night, and I'm not aware that suddenly the data has quickly shifted up in the average value because of some news event or new fashion trend or new batch of material into the factory. And as a result, like the model is making horrible predictions, and the factory is blowing up or something horrible is happening. So I can't just be asleep right now. I need to be alerted, which is what I want to talk about in the next section. So I've got code here, which I'm going to leave as a challenge for you guys. This would be to build a drift detection system. So fill in the gaps in this drift detector, which continually take in the data, compute a running average of the mean, and see when that goes outside of some certain boundaries that are computed during the test case. So during testing, you've got like the average value of your different features. And this drift detector, what I'd like it to do is to be used when someone asks for a prediction from your API to track how that thing's changing over time. If we go too far away from the average value that we expected during training, then I want to print something like, drift is detected. I'm sure I had a line for that. Anyway, there should be a line, in here. Print like, oh no, drift is detected, kind of thing. So that's what you should do there to kind of monitor this stuff.
What is the definition of, or how do we usually characterize it?
I mean, it can. I think it's probably something that you need to tune your understanding of. So like, does it matter that like it's increased by a value of 1? Depends on what kind of problem you're dealing with, right? And what you should probably do, I think, is create an alerting system that doesn't necessarily automatically like retrain everything and do deployment, but it just makes you aware of it. So you can look into that. You can look into the performance. Maybe you can even talk to your users and say like, hey, does it feel better today than it did yesterday? That kind of thing, just so you're aware of it. But what's dangerous is that you just let this thing go and you're not monitoring it in production. And over time, it's just doing stuff you don't want it to be doing. So there's like, people talk about a hidden debt of not setting up MLOps pipelines. Because if you just set up the model and deploy it, it's out there and it's talking to your customers and you don't know what it's doing, and it might just be doing things wrong on a massive scale. So not only is the problem is not finished, it's not solved when you deploy the model. It's an iterative process beyond that point where you have to keep track of what's going on, feed that back into the product development cycle, and then continue that loop, which is shown in the diagram over here. So I'm gonna wrap up with one final thing, which I think will be a cool demo. So give me two minutes to set that up, guys. Take a look through the code, and then we'll get on to the last part where we get an alert from this, and I'll leave you with a challenge to implement the retraining. So are there any questions at this point? We've got this system set up. It's trained a model, it's deployed it, it's serving it from an API, it's accepting requests, we're logging all of them, and we're monitoring them over time, tracking how those things change. And then we're looking, okay, has this model drifted away from where it should be? If it has, we want to set up this alerting. And then maybe we'd implement a retraining to train the model, log all of those artifacts, save the model, and then deploy it. Is there any questions about that process so far? Anybody want me to dive into now? Yes.
So we built the API with Python. Would that in the real world be in Python as well, or are there other languages?
Yeah, you can build in other languages. You know, Java I think is pretty popular. But there is a massive trend of things moving towards Python, especially as you know, Python becomes so valuable as a language for data science because it's cheaper to hire people that know one programming language rather than pay a premium for specialists who know both. So it's nice if your whole team can be on one continuous stack. Cool. Yes.
Once you get an alert and you want to retrain the model, do you use only the production data, or do you use all training data and production data as well?
Yeah, so the question is, when you get to retraining, do you just use production data? Do you use old data? There's like a whole body of work on data curation, which is a big part, which I haven't highlighted here, which is set up at a lot of companies, right? So people talk about most of what machine learning models do, most of the programming in them is the data. The data programs the models. So, you know, do you have enough data that covers edge cases? Do you have enough data that is, you know, that is fresh and relevant? And so in different domains, that can look very different. It might be, for example, in the self-driving vehicle domain, you want to have data which is, you just want to have all the data from all the previous examples, or maybe you just want the edge case data because that's the hard stuff. And so that would require, you know, the past 10 years. Or maybe you're working in the social media domain and you need stuff which is really up to date and fresh, in which case you might only want to take a recent part of it. That can be very independent though. But then again, there's a whole spectrum, right? Because you wouldn't want to go to the recent end and say, okay, we're just going to use data from the past 2 days where this massive event happened, and suddenly it's like only good for that event, and the event's already passed. So maybe some combination of the both. Maybe I think this will be part of the iterative process that you'd have to set up through monitoring. So when you get the model out there, you can get that feedback of like, right, it looks like training on just a week's worth of data isn't good enough. We should try and extend that. We should measure our user usage patterns. We should measure all different kind of stuff to make sure that we've got this configured correctly. Yeah, it's becoming more of a science, but a lot of it is iterative. Cool. Any other questions? It's probably a good point to kind of do final questions before I do a cool little final demo. Great. Cool. All right. Well, we'll move on and we'll wrap up then. And the last thing I want to wrap up with is this alerting. Something goes wrong, data drifts out too far, model starts behaving badly. What do? I want a phone call at 2 a.m. on a Sunday morning telling me, Harry, you need to go online and you need to fix whatever's going wrong with this model. Maybe some of you running companies, maybe some of you have something in production which you need to be aware of how to do this. And so what I want to show you now is just a tool which I really like to use called PagerDuty, which can be used to do that kind of communication. So I'm going to quickly set this up. So if you go to pagerduty.com, then you guys can create an account here. But PagerDuty is basically a service for logging incidents and notifying the right people that need to. So I'm going to log in a different account. And this is what PagerDuty looks like on the inside. So you can see a series of incidents of things that have been raised, issues which PagerDuty has been alerted of, and it's notified me or my team of. And each of those comes from a different service. So a service is something you set up. You might have like my production machine learning model service, and that's something you can send an event to if there's an issue with that particular service. So I've already set one up, but it'll be very easy for you guys to do. You just go new service and then go through the details there. But once you've set up a service, you can use some integration to connect to that service, to talk to it and basically say, well, do anything really. You can ask it to trigger an event, resolve an event, all that kind of thing. But in here, this is what a service looks like, one I've set up for this demo. If you click integrations, then you can see all the different integrations which you've got. You can set them up to, this one's just integrated with Python. So there's a Python library, which we'll look at in a sec, which can talk to PagerDuty. It's just an API, PagerDuty. It's just something, again, a computer running somewhere. You send requests to it, it processes them somehow and sends you a response. In this case, how it processes them is it calls your phone and tells you the message. Or it sends you a notification, or it sends you an email, or whatever you've configured it to do. So you can set up integrations not just with an API to use the programming language, but for other things too. If you hit add another integration, you can see it integrates with all kind of things. So maybe you've got all of there's Prometheus, like I talked about earlier. Maybe you've got Amazon CloudWatch, which is their logging service. Maybe you've got whatever. Maybe you just want to know when you get an email for some reason. So there are loads of different integrations which you can use to interact with these services. Once you set one up, you can go here and you can get your integration key. This integration key, which I'm going to copy now, I'm going to delete it after so you guys can't spam it as well. But this integration key is your password. This is what we need to put into our code, which PagerDuty will use. So I'm going to put that in here. And I'm going to, then I have to write these 2 lines of code. I've got to create a new session, which is kind of like my API client, and then I can trigger an event. To do that, we just look at the documentation. It's pretty simple. Okay, it says, I know I'm going to need this thing, but if I didn't know that, I would just, Control F, trigger event, something like this. Okay, I'll scroll through. All right, trigger and resolve an alert. This looks good. So this is how I trigger an alert that says the server is on fire, and this is how I would acknowledge an alert programmatically. I just want to use this one for now. So I'm gonna take the thing I just copied, put it into here. So that's how you use it. Use this library called PD-Pyres. It create an events API session, and you pass in your API key like that. And then back to the documentation, the next line was this one. So this is how I trigger an event like this. So I just take my event session. This is my API client. It's the PagerDuty API client. It has all of the useful stuff you want PagerDuty to be able to do, all the actions you want to be able to take as methods. And under the hood, they just make a HTTP request to the PagerDuty API. So in here, I might have something like, say, model drift detected. That's going to be the name of my event, which I get. And on the right-hand side, I think this is like the, I don't know actually what that is. I'm not sure what the right-hand side parameter is, but I assume that's like someone trying to show that it's an IP address. Basically some extra information. The key thing is like this. This is going to tell you what the message is. Depending on how you've set up your service, it might be very obvious. In my case, there's only one thing that can trigger an event. So if I've got the name, I know which event I need to look at. So that is all good. To do this, I know I'm going to need to pip install that library, PD-Pyres, run that. But now, this should work. So imagine we've set up our drift detection system. We detect a drift. This is the code which you want to have in a function, which is to alert people. Let's run this. Do not disturb. Okay. I'm going to run this cell. And if we set things up correctly, which we have, because I just got a call and it was on Do Not Disturb. I want to show you guys from end to end. So quickly, we can see incidents here. This has been triggered. I think we just need to give it a second. Okay, I'm going to run this again. Is this triggering? Or have I set something up wrong? PagerDuty calling.
PagerDuty alert. You have 5 triggered incidents on demo. Press 4 to acknowledge all incidents. Press 6 to resolve all incidents. Press 8 to escalate all incidents to the level 2 on call. Tim Howe. Press 0. All of the incidents were resolved. Goodbye.
That's how PagerDuty works. I'm gonna do it one more time because it's nicer when it says the name when I haven't got a backlog of incidents like that. But again, we've got the model set up. We've got the drift detection in place. Drift detection occurs. This code runs. It's my silent mode. Silent mode is off. PagerDuty calling.
Duty alert. You have 1 triggered incident on demo. The failure is model drift detected. Press 4 to acknowledge. Press 6 to resolve. Press 8 to escalate to the level 2 on call. Tim Howe. The incident was acknowledged.
Okay.
Goodbye.
So there you go. That's how you begin to see you can take these applications out of Python and into the real world to interact with devices you carry every day, the people on the rest of your teams, and the customers that you're serving. So hopefully, guys, that's been a good overview of this end-to-end summary of what MLOps looks like and what it is. And I hope that you understand what these different parts are and that you can go and use them to build your own products. But with that, I'll leave the rest to you. There's challenges in there, and I'll be happy to talk about anything else anybody wants to after. So thank you for your attention. PagerDuty calling. Final thing, thank you for your attention. Again, guys, if you're in London next week, or you want to be in London next week, come and join us for the first AI Insights Summit. So we're gonna be talking about some of the research that we've done recently, looking into the change of jobs in the market, what's happening, and what people need to do to position themselves for their careers in the future. There's obviously a lot happening right now in AI, so come along, be there in person with a big community of people from London, where I'm based, and I'll really look forward to seeing you there. With that, I'll wrap up.
You're going to be streaming this event as well?
I think, I will try and stream it. Yeah, I can't promise that because I'm always disorganized about when it comes to streaming, but I do have help for next week. So yeah, cool. There is an online option on there, so I think I do have to set that up. Cool. If there's any questions, guys, feel free to come and ask me. I'll be hanging around the rest of the day as well.
Thank you.